Now we have ideal gas laws as the topic for today, but I will actually want to buttress on what this statement here, gas, simply means. You know, earlier on in previous studies, we were made to understand that matter is made up of, can exist in three major states, although study has been able to explore more than three major states. Let me just highlight about 5 of these states for us. So we know we have solids, we have liquids, of which when you heat up liquids, you have gas, our subject matter for today. Then we now have plasma, which are like ionized gases. Then you have Bose-Einstein condensate. Bose-Einstein condensate. Yes. So condensate, that's BEC rather. So, but we're going to be looking at the gas today. Now, before we start talking about what ideal gas really are, let's quickly remind ourselves some of the basic components of gases. So, when we explore the gaseous state, we are able to find out there that gases, materials or substances that have a high kinetic energy, and that is why they are able to exhibit continuous random motion. You understand? Because you know kinetic energy is just energy possessed by body by virtue of motion. So if something is moving really fast or has the ability to move continuously, you say that thing has kinetic energy already. So, and that's why they have that ability to move randomly. Another reason why they can move randomly is because they have absence or weak absence, or we can say very weak, really very weak intermolecular force of attraction between their molecules. So the absence of that intermolecular force is why they can actually still move randomly. We also know that these guys are compressible. They are compressible. See that now? They are compressible. So they can be compressed. Are you getting me now? So whenever pressure is applied into a system that is gaseous, you can actually reduce the volume. And again, one thing about the gases is that they tend to assume the volume of their containing vessel. So one thing about gases is that if you put a specific amount of gas into a container or in a cylinder, they tend to assume the volume of that cylinder. So very, very important concept about gases. So that's that for a gas. Now, when you look at the top subject matter today, we said ideal gases. That's ideal gas. It simply means that we have different types of gas. This ideal here is serving as an adjective that's able to talk more about the kind of gas that we are referring to. So for us to say ideal gas, it means that we're talking about a gas that is ideal. And that means that we have a specific type of gas that we can call non-ideal gases. Are you there now? So we have other gases, non-ideal gases, or real gases. So we will expatiate more on the ideal gas. Now, what is meant by that terminology, ideal gas? So when we hear the word ideal gas, we can simply say that ideal gases are gases that obeys the ideal gas law. So those are gases that have the ability to obey the what? The ideal gas law. And we will expatiate very soon on what the ideal gas laws really are. We'll soon expatiate on that. But before then, let us quickly look at a definition of ideal gas that can bring out the property of these gases. So, an ideal gas is a theoretical. It is a theoretical because JUPEB can ask you to define an ideal gas. And when they ask you, you should be able to state it there that these gases are theoretical, or what we call hypothetical. They are hypothetical, or we can say that they are perfect gases. So whatever terminology JUPEB tries to use on you, you should be able to present it. So I don't know if ideal gases are perfect gases. Are you there now? So they are theoretical, hypothetical, or what we can call perfect gases, whose molecules have no interaction with each other, or we can use the word with one another, another. So basically, when we are talking about these ideal gases, we are going to be emphasizing on a particular property of the ideal gas that shows that they have no interaction with one another. So these gases, the molecules, their molecules do not exhibit repulsion. There is no repulsion and yet no attraction. The only type of interaction that exists between the both of them are what we call elastic collision. Elastic collision. So I want you to get it very well, magnificent students. Whenever you hear the word ideal gases, the key thing that should come to your mind is that what these gases are perfect in the sense that their molecules have no interaction with one another. There is no interactive force. There is no intermolecular force of attraction in between them. You understand? There is nothing like a repulsion. The molecules are not repulsing each other. The molecules are not even attracting each other. And the only kind of interaction that will ever exist between them is elastic collision, which is as a result of the repeated random motion that they exhibit. So that is that about the ideal gas definition or description. One thing I also want you guys to be able to note is this: a gas will actually behave ideal. Some gases will begin to behave ideal under specific kind of condition, which will include low pressure, and it is rational. Low pressure, it's very rational. How? When the pressure of a gaseous system is low, you agree with me that, look at the gaseous system here. We have a gaseous system here, for example. Let me say I cover this in this region here, and we have this pump here that can be used to regulate the pressure by pressing it down. So if we have that there, and we have these gases at these regions, we have these gases at these regions here. Now, upon contraction, or sorry, upon increase in pressure, that means if I should press this thing downward, you agree with me that this system will appear more like this. It will appear more like this. You have something like this. Let's see. We have something like this. This guy will begin to appear like this. Given that it's the same container we're talking about, we are still using the same vessel. We are still using the same vessel size. But because I pressed it down, so those molecules now will appear in this form. So you see, by pressing it, by increasing the pressure, what you have just done is that you've reduced the space available for these gases to move. You've reduced the space available in the vessel for the gases to move. And that brings all the gases closer to each other, increasing their tendency for interaction. You understand now? So because of the fact that they are now closer to each other, you've increased the possibility for them to be an interaction between those gaseous molecules. So that's that for that. That's that for that. Under these hypothetical gases, or what we call the ideal gases. Now, we said that all ideal gases will obey the ideal gas law. What are the ideal gas law? What's the basis or the foundation for the derivation of the ideal gas law? Now, we have a set of laws that JUPEB made mention of that we must talk about before I will expatiate on the ideal gas law. So, what are they? We're going to look at the Boyle's law. We'll look at the Charles law. These ones are familiar to you guys. Charles law. And then we'll look at the pressure law. And when I look at the pressure law, we will now join these two together to be able to form out what we call the what? The general gas law. Gas law. And then we will now link it to what we call the ideal gas equation. So for this first part of the video, these are the things we're going to talk about, and that will be all for this first part of this lecture. So Boyle's law, without wasting much time, you can always pause the video if there's anything you're not getting, and you can drop questions on the description below. I will read the comments, or in the comment section, I'll read your question and I will respond to you duly. Now, we know that Boyle's law actually brings into consideration how the molecules of gases tend to interact in terms of their pressure and volume. And what was he able to point out? He found out that whenever we increase the pressure, just like here now, pressure was low here. So when you increase the pressure, what happened? When we increase the pressure, that's when we're going from here to here, we increase the pressure. When we increase the pressure, what then happened? We found out that the volume did what? Reduced. Now, the volume is not the number of molecules of the gas present. For example, I can count 1, 2, 3, 4, 5, 6, 7, 8, 9. I can say I have 9 molecules of the gas here, and I believe 1, 2, 3, 4, 5, 6, 7, 8. Let's say 9 too, because the same number of molecules. We didn't change the number of molecules. We only reduce the pressure. Now, somebody might not be like, oh, the number of volume is going to be the same. No, the fact that this one has numerous spaces here. Remember, we said that gases will always assume the volume of their container. So, because the fact that the space in this side here is more, we can now assume that the volume is greater here. So here now where the pressure was low, we had high volume. So when the pressure was low, so low pressure, we said it resulted in what? High volume. And the reverse is the case, because by the time we increase the pressure by pressing this pump down, are you getting me now? We found out that what? We found out that the pressure, the volume will do what? Will increase, will reduce. So that means when we have high pressure, we automatically have low volume.